Let's look at some tricky trig substitutions, as if they're all not tricky, right? Well, here we want to integrate dx all over the quantity x squared minus 6x plus 13 all squared. So what we're going to do to create a trig sub opportunity is complete the square inside those parentheses. So here I'm going to rewrite the denominator as x squared minus 6x plus 9. So let's remember that we take the b value divided by 2, that's -3, and square it. So that's going to give us a 9. And, well, I had a 13 there, so I don't want to change the problem. So if I want the first three terms to be a perfect square, but I want the inside to still have this constant of 13, then I'm going to have to add 4. And so 9 plus 4 is 13. So this is just a clever way of rewriting what's in the parentheses so that the first three terms are a perfect square. So we're at the point where we have dx over the quantity, well, parentheses again, x minus 3 squared plus 4 all squared. So I can see, a function of x squared plus 2 squared. So I can set up a trig sub. I'm going to let x minus 3 equal 2 tangent theta. So I have a function of x squared plus number squared. So I'm thinking tangent, right? And then that number a is 2. So x minus 3 equals 2 tangent theta. Now let's take the derivative. So we have dx is equal to 2 secant squared theta d theta. And we can start making our substitution. Dx is 2 secant squared theta d theta. And then the denominator is going to be 2 tangent theta squared is 4 tangent squared theta plus 4 squared. Now that we have some space, here I can factor the 4 out, but if I take it out of parentheses, I have to square it. So that's going to give me 4 squared, which is 16. And I have a 2 in the numerator, so 2 over 16 is 1/8. Doing some mental math here. And then we have secant squared theta d theta over tangent squared theta plus 1 squared. Okay, so now the idea is that tangent squared theta plus 1 is secant squared theta, but that's being squared. And so there's 2 copies of secant in the numerator and 4 copies of secant in the denominator. So we're going to have left 2 copies of secant squared theta, in the denominator. Well, that's just cosine squared theta. All right, so from here, you got it, right? We're going to use a power reducing identity. We love trig, right? So we have 1/8 the integral of 1 plus cosine 2 theta all over 2 d theta. Pull out that 1/2, we get 1/16 the integral of 1 plus cosine 2 theta d theta. All right, we're almost there. So we have the integral of 1 is theta. The integral of cosine 2 theta is 1/2 sine of 2 theta plus c. All right, so now where are we at? We had our substitution originally as x minus 3 is equal to 2 tangent theta. We have to get now back into x. So we have to be able to find theta. Well, if I divide by 2, x minus 3 over 2 is equal to tangent theta. We can take tan inverse of both sides. So tan inverse of x minus 3 over 2 is equal to theta. So I can go ahead now and replace this theta. But what about sine 2 theta? Well, the double angle identity, right? Even more trig. So we have 1 over 16 tan inverse of x minus 3 over 2. And then let's rewrite sine 2 theta as 2 sine theta cosine theta. And got to squeeze in that plus c. So 1/2 times 2 is 1. And now I need to write sine theta and cosine theta in terms of x. Using this fact right here, x minus 3 over 2 is equal to tangent theta, we'll construct a right triangle with angle theta, and we know tangent is opposite, so x minus 3 over adjacent 2. And then we need to find the hypotenuse because sine of theta is going to be opposite over hypotenuse and cosine of theta will be adjacent over hypotenuse. So we really want this hypotenuse here. So the hypotenuse is going to end up being the square root of the two side lengths squared and added together. So 2 squared is 4, and x minus 3 squared, well, we have to write as quantity, x minus 3 squared. And if we simplify this, that's going to be the square root of, let's see, x minus 3 squared is x squared minus 6x plus 9, but then there's plus 4, so plus 13. Oh, what a coincidence. It's that same quadratic that I had at the start of the problem. And so this is my hypotenuse. So how are we going to write our final answer? I'm going to give myself plenty of space. We're going to have 1 over 16 times the quantity tan inverse of x minus 3 over 2 plus sine theta, that is, again, opposite over hypotenuse. So x minus 3 over radical x squared minus 6x plus 13 times adjacent over hypotenuse, that's 2 over radical x squared minus 6x plus 13 plus c, whoops, parentheses. And then these multiply, so the two square roots are going to cancel. So I get 1 over 16 tan inverse of x minus 3 over 2. I'm distributing that 1 over 16 now. And so let's see, this 2 and this 16 will reduce down to 1/8. So I'll have plus x minus 3 in the numerator, and then I'll have an 8 times the quantity x squared minus 6x plus 13, oof, plus c. Tricky. Trig subs. Let's look at another tricky trig sub. We have the integral of dx over the square root of 9x squared minus 24x plus 12. Well, we're in the mindset of trig sub, so we want to have something that's like x squared minus a squared, x squared plus a squared under a radical. And we saw in that last example about completing the square, but this one has this pesky 9 in front, so how are we going to handle that? Well, instead of completing the square in the traditional way, the idea is that I really want to create a perfect square trinomial. So underneath that square root, I'm going to try to create a perfect square trinomial. And remembering the fact that a perfect square trinomial is of the form a squared and then plus 2ab plus b squared. Or of course it could be minus 2ab plus b squared. So either one, right, is going to factor to a perfect square. So underneath the radical, 9x squared can be written as quantity 3x squared. And then this middle term here, if this is going to form a perfect square trinomial, would have to be, in this case, it's subtraction, so minus 2 times the value of a. Well, a is 3x, so we have 3x, and then times b. Okay, well, we need to find what that value of b is. And this middle term, to stay 24x, I would have to have a b value such that when all of these are multiplied, I get back to 24. Well, this is 6x, so that must mean that the b value has to be 4. Okay, so I've now rewritten the middle term in this kind of clever way. And what I want to happen is I want there to be a plus 4 squared. So I'm going to just put that there. I'm going to put plus 4 squared and then think about how that's different than what I have. but how much is it different? What am I off by? So 9x squared is quantity 3x squared. Minus 24x, well, this is minus 24x. And then I wanted plus 4 squared. Well, that's 16. And what I had in the original problem is plus 12. So what I'm going to have to do is subtract 4. Because now 4 squared is 16, and 16 minus 4 is 12. So I have now cleverly rewritten the part under the radical so that it will factor to a perfect square, at least the first 3 terms. These first 3 terms here are going to factor to 3x minus 4 squared. And then I have minus 4. Well, hey, that's minus 2 squared. All right. So now I have a nice setup to do a trig sub. Well, my trig sub is going to involve secant. I have an x squared minus a number squared. So I'll have that 3x minus 4 equal 2 secant theta. All right, taking the derivative, 3 dx is equal to 2 secant theta tangent theta d theta, or dx is 2/3 secant theta tangent theta d theta. So now my integral becomes 2/3 secant theta tangent theta d theta all over the square root of, all right, well, 3x minus 4 all squared is going to be 2 secant theta all squared. That's 4 secant squared theta minus 4. Now that we have more space, underneath the radical, I have a 4 in common in each term. So if I factor out the 4 and then take the square root of 4 to pull it out as a 2, I'm going to have, let's pull the 2/3 out as well. Pull out the 2 that's in the denominator, so 1/2, and then I have secant theta tangent theta d theta over the square root of secant squared theta minus 1. Well, secant squared theta minus 1, that's tangent squared theta, and then the square root of tangent squared ends up just being 1 copy of tangent, and the tangents will cancel. Again, we're assuming we're on the appropriate domain to apply these trig subs. So again, the tangents will cancel, and we're just integrating secant. So I have out here just a 1/3 the integral of secant theta d theta, and the integral of secant is natural log of the absolute value of secant theta plus tangent theta plus c. So now we just have to get ourselves back to x, remembering that 3x minus 4 is equal to 2 secant theta, or 3x minus 4 over 2 is equal to secant theta. Well, hey, that's one piece already, right? I can replace secant theta with 3x minus 4 over 2. Now it's about creating that right triangle. So if we create our right triangle here, with interior angle theta, secant is hypotenuse over adjacent because it's the reciprocal of cosine. So the hypotenuse is 3x minus 4, and the adjacent side is 2. So the missing side is going to be the hypotenuse, 3x minus 4 squared, minus the other side squared, so that's minus 2 squared. If you recognize this, this is exactly what we worked for at the beginning of the problem to turn it into that perfect square trinomial. So that means that the part underneath the radical here is that original 9x squared minus 24x plus 12. So now we can go ahead and replace our thetas with x's. We have 1/3 natural log of 3x minus 4 over 2. And then plus, opposite is that 9x squared minus 24x plus 12 all over 2 plus c. And these have common denominators. So we can combine these together and get this as our final answer.